So we made it all the way to the fourth lecture. So again, we're sort of going to come to where we can discuss tipping points as being a little bit distinct from and more general than bifurcations that we've been long familiar with. And so in particular, next one please, we'll be talking about essentially time-dependent forcing and non-autonomous and random dynamical systems. Next one please. So this is what's called again in the United States motherhood and apple pie. You know, these successful assessment reports dictated by the conference in Rio in 1992, which led to the formation of this United Nations Intergovernmental Panel on Climate Change. All talk about nonlinearity and complexity, but then they don't necessarily do a lot about it. We'll come back to that. In any case, there's a tendency to, as I said already, to proceed from discovering the atmosphere to the ocean, which was done sometime in the 70s or 80s, to additional stuff, including biota, chemistry, and so on, and to pay a lot of attention to these. Now, these words, predictive understanding, again, I mentioned already the fact that, statistical tests are wonderful, but if you really understand why something should be so, it's even better, and understanding helps. But it has, of course, to rely on all these details done better and better, but also on the thorough mathematical analysis of the models that we made. It's called commonly the forest versus the trees. You know, you have to look at each tree, but then you also have to look at the whole forest. So this hierarchical modeling approach allows one to give proper weight to the understanding provided by the models versus their realisms. Back and forth between simpler and more detailed models, and of course between model and data. And with all of this, how do we model and predict the natural variability of the system in the presence of anthropogenic? So, you know, something obvious to do is you just run your model and apply some time-dependent forces to it. That's what everybody does. But until recently, there wasn't really an understanding in the field. It's not that non-autonomous and random dynamical systems are entirely new. They go back a few decades, and then we'll come back to this at some point during the talk, during the lecture. But there wasn't really much of a realization of this point of view, this mathematical point of view on time-dependent forcing. Now you have to understand that the 1963 paper of Elio Hens took over a decade to be paid attention to by anybody. You know, there are by now, given the thousands of references to it and so on, there's been even done some history, and you know, it's very easy these days to check on the web how many times something was quoted in a particular year. But basically, the point is that the mathematical and physical community, you know, didn't realize the existence of this paper until basically Paul Martin at Harvard and Jim York at the University of Maryland paid some attention to it more than 10 years later. And then it took even more time to realize that it has something to say, in spite of the fact that I told you this model is not really a model of the atmosphere or anything like that, what the relevance of it is. So likewise, there's an evolution now in the field towards an understanding of how to digest, assimilate, whatever you want to say, this mathematics into the climate sciences. So I'm trying to show you a little bit more of that. Next, please. So basically, the idea that greenhouse gases, in particular carbon dioxide, are going to perturb the climate system goes back over 100 years. Okay? Svante Arrhenius, Swedish physicist, and some other papers more than 100 years ago. But real attention started to be paid to this when Jules Charny, who I mentioned in connection with low frequency variability and blocking and so on, and mentioned that he was the most important meteorologist of his generation, headed a panel of the National Research Council of the United States. The National Research Council is the working arm of the National Academies of Sciences, Engineering, and Institute of Medicine. And, you know, when a problem becomes important for what might happen to the United States, in particular in the sciences, and the committee formed, there's a report formulated, etc. So there was a report to the NRC, a short version of which was then published as a research paper in the Bulletin of the American Meteorological Society, BMAS, not to be confused with the Bulletin of the American Mathematical Society, about this question of sensitivity of climate to carbon dioxide concentrations in the atmosphere. So that was in 1979. And basically, the way that it is still thought to a very large extent today is in terms of such equilibrium sensitivity. So this is a graph time, and here in red is the global atmospheric temperature, and in solid and in dashed dotted blue line is the CO2 concentration. So the idea was you would double the CO2 concentration, and then you watch what happens to the temperature. And so basically, given the models existing at that time, the result was that doubling of CO2 will lead eventually to a change of 3 degrees in globally averaged surface air temperature, plus minus 1.5 degrees. Okay? So essentially from 1.5 to 4.5 degrees. And that degree of uncertainty in what is called now equilibrium climate sensitivity, ECS, I told you about the importance of acronyms in scientific language, is still of that order of magnitude. In other words, this uncertainty has not really been narrowed down. Successive assessment reports of the IPCC tried very hard, and actually this very last one, which was published recently, managed to make it look like it was reduced. But it really did so in an, let's just say, in an unobvious way. And I'm going to show you slides to this effect. But that's just equilibrium climate sensitivity. We've been talking a lot about the variability, you know, blocking events, prolonged droughts, prolonged freezing, winter, etc. What about non-equilibrium? Okay, so let's say that climate were purely periodic. So let's say, for instance, that this dominant phenomenon of interannual climate variability, which is the El Niño Southern Oscillation, were purely periodic. What would happen? Well, the mean would still go up. You know, people have what's called naysayers. English, you know, climate naysayers, and I think I mentioned that, for instance, Nobel laureate in physics, Carlo Rubbia, is one of these naysayers, so they're not all idiots, okay? Have tried to argue that something else could happen, but it doesn't stick. So the mean will go up, but then there are other things that can happen. Amplitude, the period of the oscillation can change, and that of course matters a lot, because if there's an El Niño not every 4 years, but every 2 years or every 8 years, it does matter. So finally, it's really aperiodic, so it's chaotic plus random, so it's something like this. The mean still goes up. But people don't live in the mean. I showed you the Markov chain of so-called persistent anomalies. I told you that the time mean is not really anything significant in particular. So this is really what we would like to understand, not just doubling CO2, but some sort of time-dependent behavior of CO2, aerosols, and other things that and also nature that does things, volcanic eruptions also affect climate, etc. So how do we do that in a self-consistent way? Next, please. So, okay, IPCC process results in uncertainties. Natural climate variability as a source of uncertainty, so distinguishing between sensitivity to initial data, error growth, and sensitivity to model formulation. This is really the point we want to get to. So uncertainties and how to fix them, structural stability and other kinds of robustness, and then non-autonomous or random dynamic systems. And actually, I won't have the time to go really to what happens in a relatively simple INSO model, but I will show you what happens if you add to the Lorentz convection model, this classical metaphor of dynamical systems that has been helpful in understanding difficulties with microweather prediction. How does it behave if you also apply time-dependent forces? Then linear response theory and climate sensitivity, and as usual, some conclusions and selective decline. Next, please. So there are more modern versions of this, but I sort of like this particular graph. What it shows is there was a colleague who now passed away from Scripps, close to UCLA in San Diego, David Keeling, who set up on Mauna Loa, so that's a volcano on one of the Hawaii islands, an observatory that measured CO2 concentration. The reason for putting it there is because it's about as far from anthropogenic sources of CO2 that you can get in the northern hemisphere. And then there has been also one established at the South Pole, which is even farther. Okay, so this started in the 1950s and has been continuing to the present day. I'm going to show you the next slide, which are more modern version. No, don't keep here. Okay. I'd like you to look at this, and I'm going to, obviously there's an exponential growth in CO2. Incidentally, exponential increase in CO2 corresponds to really to all other things being equal, which they never are, to linear growth in temperatures. So, exponential growth in CO2, don't run away, yelling, it's going to be exponential increase in temperatures, not yet necessarily, it's supposed to be linear, but aside from this exponential growth, you see sort of an up and down. So again, in the spirit of Fermi, what is that, in your opinion?
There is a reduction in CO2 because
you see the planet breathing. In other words, it inhales during summer, exhales during winter. But don't we know that when it's summer in one hemisphere, it's winter in the other one?
Yes, but there are the land is much higher than
right. So although biota in the ocean are very important, they only live in places where there's upwelling. So upwelling happens in eastern boundary of the oceans or along the equator. Okay, so what you see essentially is the northern hemisphere. Okay, and then well, you see that there's a little bit of this stuff also going on at the South Pole. So given these two curves and nothing else, What is the mixing time of the atmosphere? Clearly pretty well informed about everything up to this point, but this is really one that you haven't thought of before. Okay? Is it a month, a year, 10 years? Well, the answer is that it is roughly 1 year, because if it were much faster, the amplitude at the South Pole would be nearly equal to the one at Mauna Loa, and if it were much longer, there would just be no observable seasonal cycle. Okay?
Can you estimate this by, maybe there is a small shift between the maximum in, let's say, Mauna Loa and the maximum in the South Pole?
Well, if you look in greater detail, I'm sure there is. I haven't done this. It's very easy to do a correlation analysis of these two time scales. It's a very good point. But look, the point is that, since mixing is so important, I mean, we heard a whole seminar by Angelo on Tuesday about mixing in dynamic systems. And of course, mixing in the atmosphere, each time there's a big volcanic explosion, or there's some sort of, where there used to be, atomic experiments in the atmosphere. There's a lot of work that has been done on accidents, chemical accidents in wind and so on. A lot of work on mixing. But this is something that you can do just, look and think. Okay? And it gives you an order of magnitude answer. Okay, next one, please. So now, I told you that back of the envelope calculation, essentially molecular spectroscopy, says exponential in CO2, linear in temperature. Well, you don't see a linear increase in temperatures. So this is actually, some very, starting with instrumental data such as they are at the middle of the 19th century and to present essentially, you see that things have been going up and down in the second half of the 19th century, and then basically they've been going up, as I told you already, from 1910 to about 1940. And then they are they've been going down from, roughly speaking, especially in the Northern Hemisphere, between 1940 and 1975. Then going up quite substantially. Okay? So clearly, the system is not passive. There's something going on. It's pretty big. And that clearly adds to the uncertainty. Okay, so I told you it's not clear why things have been going down for over a couple of decades. One reasonable hypothesis is that at that time, the increase in aerosols, which have a negative effect on the radiation balance, exceeded the effect of the greenhouse gases. Okay?
Where the aerosol was coming from?
The aerosols, us also. Of course, there are lots of aerosols in the atmosphere which are natural. For instance, a huge producer of aerosols is breaking of waves in the ocean. Okay? But the point is that there's a change in that natural level. Okay? And I can't remember whether I think I only have a slide on that in the reserve slide. So let's not go there, maybe do that.
There is a change in the way we produce industrial power.
Well, we keep the level of human activity is increasing. Okay? So industry, the sources of greenhouse gases, agriculture produces methane, and we know that combustion engines produce CO2 and so on. So there's an increase in that, but there's also an increase in aerosols, in anthropogenic aerosols.
Yes, my question was why the production of aerosol?
I don't know, and it's not even clear that that's the reason. Okay, but in any case, you know, I think I mentioned my source for this is my former student, Irene Turk, has been very active in these sorts of things, and he says he doesn't know either. Okay, so maybe since our last lunch when we discussed this, he has found out what I haven't. Okay, the answer is that, well, you know, natural variability is not the only thing that's uncertain. What we do is also uncertain to some extent, except that's too much of it in any case. Okay. Okay, so next one, please.
I have a question.
Yeah, okay. Go back, please, for Angela. Yeah.
Which are the fluctuation, the amplitude of the fluctuations of this?
Well, you know, this is just natural variability. There's lots of things going on in the system. I keep insisting that we don't really know exactly. I mean, if you analyze sea surface temperatures, you know, we're not the only ones who've done that. There's a paper by Vincent Moreau, Bertard, and myself, I think in 1998, where we looked at this in some detail. And you see that there are certain, you know, there are certain things which are known to be to have periodic components. Remember those bumps in the composite spectrum that I showed you in the first lecture. Okay, so you know, El Nino has periodicities of roughly 2 to 3 years and 4 to 5 years, and there's a decadal oscillation in the North Atlantic, which is of the order of 7 to 8 years, you know, and North Atlantic oscillation. There are various periodic components. So there are ups and downs. This is what natural variability does. We don't know exactly. Okay? You can see, for instance, here, if you just count, you know, the number of bumps, let's say that these are pretty regular, so between 1960 and 2010, that's 50 years. Count 1, 2, 3, 4, 5, 6. You know, maybe it's 7 to 8 years, roughly.
For each point of the graph, for each of the blue graph,
yeah.
for each blue
the blue points are annual averages, and the red line is a running average of averages.
Because the average, there is a standard deviation. How much bigger are the standard deviation?
Oh, this is, look, the idea of what the standard deviation is in the running average, in the 5-year running average, is just given by the blue points. Okay? So you see that they're substantial. These are tens of degrees Kelvin, if you want, I mean, with respect to 0 Celsius. So you can see that, you know, from here to here, it's roughly half a degree. You know, this is in global average. This is serious stuff. You know, nature does something. I'm trying to tell you that we don't really know exactly what it does. Okay? But what we're talking about now is, let's say that we didn't know what it does and how do we modify it, not just as equilibrium climate sensitivity, but in terms of distribution of things and so on. Next one, please. Okay, so again, this is a graph that comes from discussions in such a National Research Council activity, but was eventually not published. There's the most common interpretation of observations and GCM simulations, or global climate model. It's actually very interesting that the acronym has been preserved, but when these were first formulated in the 70s, numerical weather predictions started in the late 60s, but these simplest climate models, like the one by Weatherhold and Manabe that I showed you, were formulated essentially in the 70s. They were called general circulation models because the purpose of the research was to understand the general circulation of the atmosphere. Now they're called global change models. Sorry, global climate models. Okay, so the purpose has shifted to determining what we are doing to nature, but we've a little bit given up on understanding what nature does. Okay? So, the most common type of observation is still in terms of a scale of linear ODE. Okay, that was the case for the first 2 or 3 assessment reports of the IPCC. So you have something like this, temperature derivative, time derivative, temperature equal minus KT plus K plus Q, and K is a sum of feedbacks, positive or negative, but linear in this interpretation, and the QJs are sources of sinks. And actually, at the beginning, the chapters of this assessment reports were essentially given in terms of expertise on particular feedbacks and particular sources and sinks. Okay? So this is just, again, a simplified graph of the one that we saw in detail before. And this is what the linear greenhouse gas effect would give you, and this is what you observe. Clearly, we need to consider instead a system of nonlinear PDEs with parameters and multiplicative as well as additive forcing both deterministic and social. That's the level of understanding that we're trying to bring to this problem. Next one. Again, these are out of the encyclopedia arguments. Okay, so this is the type of okay. I told you that there's hundreds of people, even more, involved in these assessment reports. They are second-order acronyms. So this is the Intergovernmental Panel on Climate Change. This is the 4th assessment report. Working group 1 is the one that deals with physical effects. 2 and 3 deal with more socioeconomic stuff, impacts, adaptation and mitigation. And this is summary for policymakers. All these acronyms, are familiar to anybody who's involved in this. Okay? So I like this one, although there have been additional ones because it's very clear. What is seen here is essentially simulation. So at the time, there were, I think, about 12 GCMs, now Earth system models involved. By now, there are, I think, something like 3 dozen. There were for a while 2 dozen of these. And so basically, these are not genuine error bars, they're just a distribution of the results of the different big models involved in these assessments. Okay? Now, why do we have more and more of these? Of course, because the problem is important, but also because if you want your agency to have the next biggest civilian computer, you have to participate in these exercises. Otherwise, your government won't give you money. So, I've started, except for being the reviewer for the first couple of assessment reports. I have not participated because it eats up a lot of time. But I have been the chair of the Scientific Advisory Committee to what is more or less the US National Program for Climate Simulation. You're not allowed to call it that because of different agencies and different, okay? The so-called Climate System Modeling Program centered at NCAR. And, the truth is that NCAR scientists did not want to participate in the next assessment report. They wanted to do what GCMs were made to do, study the general circulation. But they wouldn't have got to the next big computer. So the idea is that, yes, you are going to do these simulations according to certain protocols, and then you are going to have the time to do the science, really look at the results. Except that it works like for NASA. I think I told you about it. NASA, every time for every satellite or whatever spaceship that it sends out to some planet, has 10% of the budget set aside for analyzing the results, except by the time that you have the results and want to analyze them, the next project is being worked on and it's going to gobble up the money that was set aside for it. So, this is not necessarily, I'm sorry, there are lots of very, very good scientists participating in these assessments, and they're doing so out of deep conviction that it's important for humanity, etc. But you will see that it tends to overrepresent people who are involved with big models. Okay? So anyhow, what we're looking at here is about a dozen such models, and each one of these colors is something that was called at the time a scenario. You know, we obviously don't know what humanity will do over this coming century. Okay? Not even you, I hope we live to the end of the century, know what you'll do. Okay? So these were called scenarios. Now they're called RCPs, like a representative concentration factor. This one is what would happen if we were particularly wise and just stopped increasing, spewing greenhouse gases into the atmosphere. And this used to be called BAU, business as usual, if we keep being as stupid as we're now. Okay? So for each one of these scenarios, you know, there is this thing which is not a genuine error bar, but it's just a distribution of the 12 or so models that result for the respective scenarios. And you see that it's still a few degrees. That's why I told you the 3 degrees of Charlie et al. Have not really been reduced. Now, Pete, I cannot have cracking the same joke every time, and I've cracked it already once here. You know, we know enough to adapt and mitigate. There are other decisions that are even more important in our lives that we take with a lot less knowledge than we have about climate change. But that doesn't mean that we really understand and that we have gained a lot of certainty as we would like. Next one, please. Okay, so, you know, graphs like that keep getting done. This is from, in principle, these assessment reports should be, according to the Rio Convention, which has an unpronounceable acronym, which is all consonants. You know, those people have not thought about having a good acronym. Very important. But according to that convention, this should be done every 4 to 5 years, except that it's a huge effort and sometimes it takes longer. So this was, the previous one was AR4, published in 2007. This is AR5, 2013. Again, working group 1, summary for policymakers. Incidentally, somebody that I'm sure some people here know, Uriel Frisch, you know, important turbulence physicist, once told me, I mean, he's not involved in climate per se, that he tried to read one of these summaries. These summaries are supposed to be written for heads of government and heads of large companies and so on, okay? So he tried to read it, and he says he didn't understand it. So I really wonder what those people for whom it is written do with these things. Okay, so you see that it's still global average surface temperature change. Okay, again, these are, as I told you, they're no longer called scenarios, they're RCPs. This is the worst one, and this one is the best one. And, you know, you see that there's still quite a bit of distribution. Now they also look at sea ice extent, global ocean surface pH, acidity, which tends to destroy coral reefs and so on. So the uncertainty persists. Next, please. Okay, so just to give you a little bit of background, and now we'll start talking about things closer to the science. Natural climate variability as a source of uncertainty. So, sensitivity to initial data. Next one. So, aside from that, you know, divergence of trajectories in the Lorentz convection model, this is from the European Center for Medium-Range Weather Forecast, because of the uncertainties in initial conditions, as well as the instability of atmospheric flows. What one does now is not single forecast, but so-called ensemble of forecasts. So this is 50 forecasts. You know, the European Center produces every day 10-day forecasts with 50, I mean, the same model, but with slightly different initial data. And this corresponds to a particular storm called Lothar, okay, that basically caused a lot of damage throughout Western Europe. I can tell you that actually, so this was Christmas, basically Christmas Day of 1999, the last Christmas of the previous century, forecast time T plus 42 hours, okay? So that's almost 2 days. The deterministic predictions, so remember that these are again sort of streamlines, deterministic predictions, and this is what's called the verification, what actually happened. Big load here, and as a matter of fact, it blew the roof off my office as a visitor at the time was on the top of the building of the physics labs at the École Normale, and my own office was not damaged, but the one of Olivier Talagrand next to mine, when he came back from vacation, you know, he had a lot of stuff spread out on his floor because he's a little bit of a messy person, and you realize it's wet. It actually rained inside his office, and a lot of trees were blown over. It was a serious event, and this is what the different forecasts did. So it's very interesting that some of them actually predicted the storm even stronger than it occurred. But then a lot of them, you know, didn't predict much. And yeah, well, something which this one almost did it right, but you don't know in advance which one it will be. Okay? So this is uncertainty with respect to initial data. Okay, as Poincaré said in, I forget the exact date that Sciences et Méthodes was published. Next. So actually, this is just to point out that it's not exactly exponential divergence, it's versus coarse grading as we discussed in the second lecture. Classical dynamics is a positive geometric trajectory divergence exponentially. This is from Lenny Smith, a colleague who's actually an American, but working at Oxford and at the London School of Economics, and published in the same Encyclopedia of Atmospheric Sciences, which also some stuff that I showed you published. So, you know, if you start something like a pretty pointed Gaussian here, what will happen as time runs in this direction is that as you cross from one wing of the butterfly to the other, in the intermediate term, you know, you will have bimodality, but actually eventually this washes out. I have a little problem at the end to you might want to look at. Okay, next one, please. So this is uncertainty with respect to initial data for the same model. Next come to uncertainty with respect to the model. But, okay, this is also a table which I think was done for the first time in this fifth assessment report. Phenomena and direction of trend. Okay, warmer and fewer cold days and nights, warmer, more frequent hot days, heavy precipitation, etc. Likelihood the trend occurred in the late 20th century, typically post 1960, of human contribution, of future trends. So there are things like very likely and virtually certain, and then there are some that say more likely than not. In other words, if you flip a coin or you run 20 very big expensive models, you get about the same level of certainty. That's a little bit unsettling. It doesn't say that it's useless to run the big models, but it gives you pause. In any case, it says that randomness has something to do with it, which is what Poincaré said over a century ago. Next. Okay, so we're moving now from this sensitivity to model formulation to uncertainties on how to fix them. Okay, next one, please. Well, this is actually from the United Kingdom Met Office, which is one of the big operational numerical weather prediction centers. Again, this is borrowed from Lenny Smith. We were both at some meeting in Sweden. And, you know, it's actually quite amusing that the UK Met Office does produce charts where you can look up the district in which you live and say within a certain 5-year span at the end of this century, what temperatures will be like. They obviously do that because the ministry on which they depend tells them to do it. What it means is not clear. Then they have a pie chart which says, you know, where the uncertainties come from: internal variability, carbon cycle, structural uncertainty. I don't know what they mean, but for, you know, dynamicists, it means structural stability, okay? In the sense of parameter uncertainty, downscaling, etc. So precipitation changes for the 2080s relative to 1960-90 at the 25-kilometer box A southeast end. So there's one which has structural uncertainty. Okay, next. So how can we lay our hands mathematically on this sort of structural uncertainty, or uncertainty with respect to parameter values, etc.? So here we start with non-autonomous dynamic systems. So let's just look again at the scalar linear ODE. If sigma is equal to 0, we all know what happens. It asymptotes to 0. But if it is not equal to 0, what happens? How do you define attraction in this setting? Okay, for autonomous systems, you just sit in a certain point and you look whether the trajectories converge to it, and that's a story, diverge or whatever. But here, the forcing changes. So what do? Let's say that this is the observation time, okay? And you want to know what is supposed to be the counterpart of your concept of a fixed point. You know, sigma is 0, there's a fixed point, x identical to 0. Well, what you have to do is to pull back, and technically speaking, to some compact set, never mind, and let it rip, and you see that it will converge to a point, and then if you do the same thing over here at some other point, and these points line up on a straight line. Okay? So, which in this case, you can just compute analytically. Let's see, can you switch to the short one of the two videos? Yeah. No, no, not this one. No. The other one, which is PDA movie, so PDA movie.
Let me change it.
No, it will, the VLC will, okay, whatever. Okay. So, you see, this shows how you pull back. So basically, wait one more. Okay, you pull back and you see that things, as you pull back further, converge to the straight line. Now, that's enough. Thank you. Let's go back to the slides. So this basically says, first of all, it says why this is called a pullback attractor. You have to pull back. But in addition, it says that while forward asymptotic motion involves only one parameter, here the one parameter semi-group of autonomous deterministic dynamical systems has to be changed to a two-parameter one, in which you don't have just a forward t, but also the backward s. Okay, next one, please. So, we've just shown that x of t and s for a given x naught minus this a of t, so the a of t is this thing, tends to 0 for every t fixed, and for all initial data x naught, okay, within a compact set. We just encounter a concept pullback attraction, and here a of t is pullback attraction. So what does it mean physically? Next one. Okay, the pullback attractor provides a way to assess an asymptotic regime at time t, the time at which we observe the system starting to evolve from the remote past s. Okay, so the time t at which you observe is called typically a snapshot. Since the attractor itself evolves in time, you have to look at slices of it. So this asymptotic regime evolves with time. It is a dynamic object. Dissipation. So again, the fact that alpha was still, that the coefficient was negative is essential. And it plays the same role as for strange attractors. In other words, again, in Hamiltonian dynamics, don't have attractors, you have invariant sets, but not attractors. So this, well, there are things that can be said about Hamiltonian systems as well in this setting, but we're not going to go there. Next one, please. Okay.
This is the next one for you?
Yeah, this is the next one. This is
so probably there is some, I don't know.
Yeah, it might be that the slides are, you know, it has to do with the fact that I give too many talks and I cannot rewrite each time everything completely and they just shift slides in and out. It has never happened to me, but okay. So a little history of climate and stochasticity. This actually comes from general audience talk that I gave at this Research Institute on Mathematics and Statistics in 2013 in Kyoto. So, okay, our modern ideas of stochastic processes essentially start with this, one of these three papers Albert Einstein wrote in 1905, the one on Brownian motion. And then, well, interestingly, during World War II, when all sorts of terrible things were happening, also something good happened. So Ito formulated a calculus now named after him, which enables the solution of stochastic differential equations. So lemma is essentially the stochastic counterpart of Leibniz's changeable differentiation. Now, what about the relevance to climate? So it took again over 30 years. Klaus Hasselmann described climate, essentially Brownian motion with weather as stochastic driver. So in this view, the deterministic part of the model is stable, so it's like the minus alpha x that we had in the previous thing, and random perturbations decay to the mean. Okay? So they still fluctuate, but everything is essentially decays to the mean. Next. Okay, so let's see whether we could now come back. I think that everything else will be this one. I don't know this time. Okay, so the theory of random dynamical systems is essentially the counterpart for randomly formed dynamical systems in the geometric theory of ordinary differential equations. It allows one to treat stochastic differential equations and more general system theory like noise as flows in phase-space cross probability space. So, you know, these are vague ideologies, SD analogous to ODRDs to DDS. And Ludwig-Einhold to VII. That's obviously a joke, but you know, I don't know how many of you know Ludwig-Einhold's first book on linear stochastic differential equations, which was a nice thin book, very readable. And then this one is something big like this, and it's not terribly readable. And as a matter of fact, I remember that I think we had an exchange with Ferrangelo Liberani about this meeting of INDAM on hyperbolic dynamics, which was held that year in Coronado, and where Lai-Sang Yan decided for the first time to invite some people who are not the traditional participants in that biannual meeting. And when I gave a talk a little bit similar to this one, you know, Lai-Sang told me, Michael, you have to understand that even these dynamical systems people don't understand very well random dynamical systems. And so don't be afraid, you know, we've tried to make this more understandable, but there is somebody, you know, just down the street who has made fundamental contributions to this theory, so you can go and listen to him. That's front of fun. Okay, next one. So aside from these vague analogies, what is a setting? A phase space X, say Euclidean, a probability space, and I assume everybody knows about that. So the omega and F and P, the sets, the probability on it. For example, the Venus space in which these are continuous functions of T in this space with being a measure P, and the model of the noise. So this is now where things become a little bit, you have to pay a little bit of attention. So this is mapping omega into itself, preserves measure P, and it is called the driving system. So example again, Wiener process, okay, where you have this invariance property of the driving system, okay, that this is equal essentially to this difference, so you can start the noise at S instead of T equals 0. And then a mapping on all of this, R for the time and omega for the probability space and X for the space, to the phase space, which has a so-called co-cycle property. This, a good example, is the solution operator of this. Now, what is the co-cycle property? Next one, please. So these figures are actually taken from a paper in which essentially in Physica D, a special issue that Muriel Frisch was organizing for the tricentennial of Euler's birth, and in particular 250 years since his work on fluid dynamics, they call them Euler equations, and where he and his associate editor encouraged us to use some figures to explain because of the difficulty of this stuff. So, you know, up till that point, this work was done by real mathematicians, never a figure, okay? So what you see here is the driving system, okay? Omega, which is a realization within the capital omega, which is evolving with this theta s. And the co-cycle property essentially says, so these are copies of the phase space X at these different times. And the co-cycle property says that going from here to here and from here to there is the same as going from here to there in just one step. So this is what's called in deterministic dynamics essentially the semi-group property. Okay? So phi is a random dynamical system, and this theta is a flow on this bundle, okay? This family of copies of X that evolves with theta X. Next one, please. Okay? So a random attractor now, so this is now the generalization of a Kullback attractor, which I illustrate to you in that very simple example. Random attractor A of omega, a particular realization. You have to understand that this is very important. This talks about particular realizations of the noise. It is very different from the Fokker-Planck point of view, in which you just look at the whole distribution evolving forward in time. And I hear this concept of Kullback, and the single realization is very important. So random attractor is both invariant and Kullback attracting. So the invariance is essentially this. Okay, if you apply phi at t and omega to a omega, it's the same as getting a of this. And attracting, so for every compact set B in the remote past, the limit of this distance goes to 0 almost sure. Okay? So instead of just having a straight line as we had in that first example, very simple example, you have something that can be pretty complicated. You're going to see what happens in the Lorentz system, the Lorentz convection model, if you add random noise. But for a certain snapshot, you have the same kind of convergence that you saw in that little video.
Excuse me.
Yeah?
Almost assured with respect to what?
Pardon me?
Almost assured
With respect to P.
the probability of the...
With the probability on omega. Yeah, yeah. which is not necessarily the weight measure, but you might just as well think about it for the moment.
Yeah, but in Europe, since this aerodynamic system, you think that P will be something by the measure, or just looking at the Raman system?
Well, look, what you do numerically is always what you do numerically. Now, the mental picture that you have of that, has to be somehow in accordance with what you're trying to model. Okay? But at this level, it is just a measure P on omega with the Borel sets F, etc.
Yes, usually the system, the current system is simply all that.
Yeah, well, okay. Actually, yeah, actually the interesting examples is when it's not, but no, I just tongue in cheek.
Okay, no, if you want to prove something.
Yeah. If you want to prove something, it helps that it be agnostic. Yeah. Okay. Okay. So now I'm going to the next one because it's something very interesting happened. But think about this for a moment as being just a snapshot still out of a video. Okay, next. Okay, so we're going to discuss what happens when you perturb the Lorentz convection model. Next, please. Okay, so again, in this case, so a pullback attractor in the random case is called a random attractor. So this is a snapshot of this random attack computer fixed time over the same realization. Omega is made up of points transported by the stochastic flow from the remote past. Now, again, in mathematical theory, you have to let S go to minus infinity. In practice, in order to carry out numerical computations, you have to know how rapid the convergence is. So that's still a somewhat open question, but we're working on it. In any case, I want to tell you that when we became interested in this problem, as far as we could tell, there was a single plot of a snapshot of a random attractor in the entire literature. Due to a German applied mathematician, Schmalfuss, and it was a lot ruder than this one. So what we do here is we use multiplicative noise in the deterministic noise model with the classical parameter values for which you have a strange attractor that you know well, and compute these things pathways. Next, please. Okay, so these measures are typically called in the literature disintegrated measures, which is not terribly helpful. We prefer the name sample measures, which is used by Lyson Young, which is much more suggestive. Okay, so this is it's a projection onto the XZ plane of the invariant measure, okay, at a certain time, fixed realization. And so we show this projection with multiplicative noise. So it's X1, 2, 3, in other words, XYZ, plus alpha, Xi, and Wiener process. Okay? And so 10 million initial points have been used for this picture. It looks pretty ferocious. These are obviously the convective points from which Hopf bifurcation, subcritical Hopf bifurcation occurs in the deterministic case. Okay, next one, please.
Can I ask,
Yeah.
what is the scale of the colors? Like when red is more.
Yeah, I'm sorry. When we did this paper, so this is basically out of a paper with Michael Shekun and Eric Simonet, which we put into that special issue. No, it's a subsequent paper. Sorry. The special issue for the Euler issue that was done by Uriel Fraser is 2008. So it was also with these two people, Shekun, Simonet. At the time, Michael was my PhD student, but Eric Simonet my postdoc. This is on a subsequent paper, also in Physica D in 2011. And frankly, at the time, we didn't quite realize how interesting this was, or didn't pay enough attention, and we don't have really the color scales. But basically, this says high density, and this says low density, and of course, here low density.
Red is highest density.
This is the highest, and this is the lowest, which fades into none.
But black is low density.
Well, let's look at the next one. And then, sorry, we have different colors. You know, not all of these are the same aspect ratio and the same colors. I apologize, but I don't have better ones. This is 1 billion. So that was 10 million, 1 billion. Now, the important thing is alpha here is not small. Okay? Alpha equal to 0.5 is comparable to the sizes of X and Y. Okay? So here, this is even more ferocious, and what you see is that indeed there is a formation of the unstable manifold. Okay, there's a lot of filamentation here. See, I used to not pay attention to random stuff because the common opinion, as for instance demonstrated by Yuri Kiefer, if you just put some additive noise that will just smear out instead of having a Cantor set. If you drill through the wings of the butterfly in the Lorentz attractor, you have something that looks like a Cantor set, so it will just get smeared out. Okay? Well, that is not at all what happens in this case. Okay? So there you have a lot of interesting structure. Next one, please. Okay, so these sample measures are the frozen statistic at time t for realization omega. How do they evolve in time? So now please show that video. Yeah, okay. Show the next slide because it'll, okay. So this is just one snapshot. Again, it's different. It's again different colors. I'm sorry about that. Okay, so this is what I call the day in the life of the Lorentz model's random attractor, or more forth. See supplementary information Shekousi Mornay did 2011. So that is only a fairly short video at a low resolution that was tolerated by the journal, but there's a high quality video movie which you can find here on the website of Michael at UCLA. So in the meantime, let's take it's going to be better if we do it from this laptop. So what you see is quite clearly you have advection of the invariant measure by the deterministic flow. But you also see things like this, like this Artesian fountain, which are totally unsuspected. So here the interaction between, there's also a slight flimmer, which is just the random fluctuations. And, but on top of these two things, advection of the measure and a flimmer, there are things that you wouldn't have suspected at all from anything that you knew about random dynamical systems, Lorentz system, or whatever. So, okay. So I think we're going to stop here for a 10-minute break, as usual.
I have a question.
Yeah.
When you take the Lorentz equation with the noise, the component of the noise is the same for all three?
Yes, in this case, it is, well, in random dynamical systems in general, like in stochastic differential equations in general, it doesn't have to be the same one in the three equations. Here it is. We just did it that way. The one who did the calculations originally was Eric Simonet, but by now Michael knows very well how to do That's why there's a version on his website. This is pretty exciting stuff. It's actually very interesting that we got inquiries after the publication about, just how we did it, and could the person who is writing have a copy of it? And then there was an exhibition of computer art in Paris where we wanted to have a copy of it. And Michael and Eric are somewhat reluctant to share this with people who might want to make commercial uses of it. Okay, so anyhow, but no, it doesn't have to be the same. It can be a vector Wiener process that has different components. Okay, so come back in 10 minutes. Okay, then in the mathematical literature, Probach attractors, so I mentioned Ludwig Arnold and Franco Flandre. In fact, this paper, which was published originally as a technical report of the Scuola Normale here in Pisa, done by Hans Kaul and Franco, who were postdocs of Ludwig Arnold in Bremen. And although this is the earliest reference, the one that is usually given is a later journal publication by the same two authors, etc. The physical literature, there were Czesław Grzegorz et al. On the postdoc of theirs, Merz, who wrote in PhysRev A a paper called Multifractal Properties of Snapshot Attractors of Random Maps. Now, clearly these people had the same basic idea, but being physicists, they were more fearless, and the definitions are not as careful. And also the word is different. You see, for Hans Kaul, I think I haven't met, and unfortunately I haven't met, this issue of the Probach, how do you define the damn object is very important. For the physicists, it wasn't. They just said, snapshot, we have something that attracts to something at every point in time. And when we started working on this, okay, so I say, well, the first thing is also stochastic on top of random attractors. So, when we became interested in this, because of these issues of robustness of the model with respect to the issues of anthropogenic and other changes, since we're all, we had all PhDs in mathematics, we started with this version, Probach attractors. And then at some point, I got to review a paper by Thomas Tail and two of his PhD students, or I think this was a PhD student, this one was a postdoc, in which they talked about probabilistic concepts and changing climate, a snapshot attractor picture. So clearly Thomas Tail was aware of the work of Ed Ott. Okay? So in my very positive review, and also never contributed to the publication of the paper, I sort of told him, look, there are these other things that one can think of. But it's amusing that we use the word snapshot for the stills of the video. We just call them snapshot. Now, these two communities, going back to 1967 in mathematics, and at least 1992, specifically for the random dynamical system situation on the one hand, and to 1990 in the physical literature, never communicated with each other. It basically took Thomas Taylor need to communicate what are the climate applications to become aware of the corresponding work on the other side of the fence. Okay? So this is pretty amusing because, as I said, we talked about pullback and random attractors and Thomas and company about snapshot attractors, and they are basically the same thing, except that the snapshot ones were not as carefully defined. There were no theorems proving them. If you don't define things very carefully, you can't prove theorems, right? Okay, so that's it. Sometimes applications can have also implications. Okay, next one. Okay, so linear response theory and coming back to climate sensitivity. Next one, please. Okay, here I'm just reminding you of the so-called equilibrium of climate sensitivity and this version that we're really more interested in. Okay, next one. Okay, so classical strange attractor, physically closed system modeled mathematically as astronomers. Neither deterministic nor random forcing, but I'd say here, well, it's not entirely clear that humanity is deterministic, nor that nature is random, but let's say these are plausible approximations. The attractor is strange, but still fixed in time, and I say this is analogous to the irrational numbers. You know, humans don't like things they're not familiar with, so they give them bad names. Natural numbers 1, 2, 3, and then rational numbers 2 over 3, 7 over 17, etc. Okay, and then there are irrational numbers. Attractors, strange. In this context, climate sensitivity is essentially the change of the average value first moment of the coordinates as a parameter lambda changes. Next, please. So, random attractor, a physically open system modeled mathematically is non-autonomous, allows for deterministic as well as random forcing. Okay, so these are just snapshots out of the video. The attractor is pullback and evolves in time. It's like an imaginary or complex number. It's worse, but more interesting. Climate sensitivity now, the change in the statistical properties first and higher order moments of the attractor as one or more parameters change. Okay. So let's now apply this to spatial temporal evolution of an ENSO episode. Next one, please. First of all, okay, how many people have heard about the medium sudden oscillation? Good number. Okay, it's in the media. Not just in the newspaper, it's in the stuff. So what is it? Well, this is based on a review paper of Jean Rasmussen and associate in the Monthly Weather Review in 1982 when there was a particularly big one. Basically, you're looking at the tropical Pacific and the color here indicates this is a warm anomaly and this is a cold anomaly. So again, anomalies are just differences, in this case, between the mean monthly map and the climatological average for that month. And I told you, climatological average mean of 30 years of data. So it shows what's called a tongue of warm water advancing westward along the equator and intensifying. I think these are anomalies of about 2 degrees in water temperature. That's pretty substantial. Okay. And then a fairly sudden collapse, and we have cold tongue. Okay. So this happens typically, this is the picture in March, May. Okay, so these were composites for 9 ENSO episodes available at that time. This is March to May, August to October, December, February. And so incidentally, it is called El Nino. So El Nino is the oceanic phenomenon, the southern oscillation is a corresponding phenomenon in the atmosphere. It's called El Nino by Peruvian fishermen because something like this happens every year around Christmas time. Okay? So this December, January, and then again the following May, June. Okay? So this particularly strong version of this happens from time to time. You know, it's sort of amusing that the way science is written, in lots of places you'll say that it happens every 4 to 7 years. That's clearly false because it depends on how long the history you look at. Okay? And since it's irregular, it happens irregularly. And in particular, during the 90s, there was very little of it. Okay? So, next one, please. So this is this is about parameter dependence. So this is from a particular model that was developed by Feifei Jin and David Nealon, and this work in which we looked at seasonal growth. It's very interesting that in spite, I became interested in this ENSO stuff precisely because at the time, in the early 90s, the phenomenon, in spite of the obvious importance of the seasonal forcing, it's called El Nino because the water is warmest off the coast of Peru in December. The phenomenon was treated as autonomous. Okay? The main point was to show that there is an intrinsic periodicity, okay, which is of a few years. So these papers, 1990, so Jim and Nealon, Feifei Jin was first my postdoc, and then we started also working with David, and then finally we did some things, the three of us together. I mentioned the paper Feifei Jin in connection with oscillatory behavior in low frequency atmospheric area. So there are actually 2 papers published in Science back to back in 1994 about the effect of the seasonal forcing on the oscillator. And we just used essentially that model and we added seasonal forcing. And so what you see here is one of the variables of the model. I don't even remember exactly which one it is, but it's probably temperature. And the time scale here is in years. So you see 90, 100, these are tens of years. Okay? And so the question is, as a function of this parameter delta, which has an effect on the periodicity of the intrinsic oscillation, what is the behavior of the model in the presence of seasonal forcing? So what is shown here is the skewness, in other words, essentially the third moment and the fourth moment, suitably normalized, as a function of this parameter. So, in general, in working with big models, it is assumed that the dependence on the parameter is smooth. Again, mathematically, what you like to prove about partial differential equations is existence, uniqueness, and continuous dependence on parameters. Okay? And so you see here that it can be smooth or it can be rough. I mean, there are intervals of this where it is pretty smooth, and then there are jumps, and then it can be pretty rough. So since this is a delicate matter, and the model is very nonlinear, and so on, sometimes it's 4,000 years, we ask ourselves a lot of questions, and in particular, this shows that these changes in behavior with respect to the parameter are not just artifacts of the numerical implementation. These parameters which deal with higher order moments behave in exactly the same way. Okay? So, next one, please. So that model, this Jim Milling model that we used there was what's called an intermediate model within this hierarchy from the simplest to the lower to very complicated, hence billions of variables. But this is an even simpler one. It's a so-called neutral delay differential equation model of ENSO, using delay differential equations of the model of ENSO goes back to the late 80s. And it doesn't really matter exactly, it's derived from a particular model that KZDF, which is the first one that was used for dynamic forecasting of interannual climate variability. And so we're adding seasonal forcing, which is given by varying this parameter mu. So mu is over here, okay? We compute the pullback attractor and its invariant measures. And so here is the relative response, again in percent of height. The H is the height of the thermocline. So the thermocline, if this is the surface of the ocean, and this is Z, okay, depth. And this is, for instance, temperature. You have something like this. So you have a profile like this. You know, up to here is a so-called mixed layer. And then this is the deep water. Okay. So this is so-called, this thing here is what's called a seasonal thermocline. Okay, that separates the well-mixed surface layer from the deeper water. And then there is another thermocline somewhere further down here, which separates, again, two kinds of behavior of the ocean. So the two variables of this model are this depth of the thermocline and the sea surface temperature. Okay, thanks for sharing. Let's go back. Okay, so this is just a change in percent of one of these delays. The delays essentially correspond, on the one hand, to the time that it takes from for temperature to propagate down the thermocline and say between the air and the water in the model, and the other one that is much longer has to do with the waves. Osprey waves propagating westward, Kelvin wave propagating eastward along the equator, off the equator. The figure shows the changes in the mean second and fourth moment of this depth of the thermocline, along with the Wasserstein distance, dW, between the solutions, okay? For changes from 0 to 5% in this delay parameter. So again, you see that, you know, mean, second moment, and fourth moment, as well as the Wasserstein distance, seem to behave in rather similar ways. Let's go to the next one. So we have intervals of smooth and rough dependence. So the idea is how to define climate sensitivity, or what happens when there's natural variability. So one usually defines climate sensitivity gamma as a change in global temperature, as a change in net radiation. So again, I don't have my laptop to use, but that is to remind you of this picture in which mu was a parameter for multiplying the net insulation at the top of the atmosphere, and this was global temperature, and we had something like this. Okay, so if mu equals 1 is present conditions, you know, this, the slope of this curve essentially is delta t over delta q, changing the parameter. Okay, so, sorry, back to the slides. So, basically, in this case, gamma is of the order, so this slope here is of the order of 1 degree Celsius per 1% change in Q. Say that there's much more to climate than the mean, so what is plotted here is the invariant measure, okay, associated with the projection onto H, and this is for H of t, the time t, and this is ht plus 1. Very often such an embedding is done for ht minus 1, but it doesn't really matter. And so this is the variant measure. You can see that there are very high maxima. Okay, here we have the color bar. There are very high maxima in the measure. It's pretty irregular, and it's also pretty convoluted. So much more to climate than mean is the actual distribution of temperature in time and space, the extreme of temperature of precipitation, etc. So we'd like a better, more flexible definition which does take into account these details as well as chaotic behavior. So this would be essentially something like the derivative of the Wasserstein distance with respect to a parameter, at least some sort of a finite difference. Now what? Everybody knows what the Wasserstein distance is? Okay, so essentially the Wasserstein distance has relatively little to do with Wasserstein, who was a Soviet mathematician, and it was named after him by another mathematician who made it popular, Dobrushin. But actually it goes back to Monge and to Kantorovich, among other people. Monge, as some of you probably know, was an important mathematician, known, for instance, the Monge-Ampere equation and many other things. Gaspard Monge, born in Bonn, a city where they have very good wine. And he was also an officer in Napoleon's armies in Egypt. So what he defined in a memoir of the French Academy of Sciences at the time is now called very often the Earth mover's distance. It's the following thing. It's essentially a difference between two probability measures, but you can think about it, that you have a platoon of soldiers who are digging a trench somewhere here, that have some place to put the earth, so that they're digging the trench, it's more or less earth, okay? And they're trying to put it somewhere over here. And it is the amount of effort that it takes to take the earth from here to there, and it is the minimum amount of effort that it takes to do this. So it's essentially used a lot in transport theory, which is why it's so popular these days. The contribution of Kantorovich was that during World War II, he used something like this in terms of optimizing transport of all sorts of goodies on the Soviet railways. Okay, so let's just say that it's a very good measure when you operate in probability spaces. Used it with a colleague at Imperial College, Jan Krishan, for doing some work in data simulation. So again, we're looking at the difference between two such invariant measures at two different times. Okay, next one, please. So what is shown here is how this thing distorts as we move along in time. And the point is that there would be such differences not just in the height of the measure, but also in the shape of the trench in phase space, okay, as you change the parameter. So the suggestion is that instead of just taking the mean of this versus the mean of that and so on, you take actually this Wasserstein distance and you look at how that changes as you change it. Okay. Next one, please. Conclusions and references, natural variability and anthropogenic forcing. Next one, please. So a change of paradigm from closed autonomous systems to open non-autonomous ones. Random attractors are spectacular, I think, seeming useful and just starting to explore for climate applications. Work in progress, study the effect of specific stochastic parameterizations on model robustness. I mentioned to you about subgrid scale phenomena, like cloud processes, great cell applications from simple to intermediate models, big ones, application for climate sensitivity, possibly for predictability. Actually, I showed you that there was in that invariant measure one very big maximum, which is clearly the most probable time. So it is quite possible that you might be able to do better year-to-year interannual predictions of the state of the tropical Pacific and therefore the rest of the climate system, thinking in this way about things, etc. Next. So, what about, well, first of all, the word randomification are not my own. When I got a certain distinction from the European Geosciences Union, there was a press conference, and so the press agent of the EGU told me you have to attract attention, you have to use some big words. So randomification comes from that. So basically, Lorentz says, Lorentz who didn't get Nobel Prize in physics, but should have, climate is deterministic and autonomous, but highly nonlinear, trajectory that moves exponentially. Forward asymptotic PDF is multimodal. Hasselmann, who did share it, said climate is stochastic and noise driven, but quite linear. Trajectory became back to the mean. Forward asymptotic PDF is unimodal. Randomification, climate is deterministic plus stochastic, as well as highly nonlinear. Internal variability and forcing interact strongly. Changing sensitivity refer to both mean, higher moment, distribution of extreme events, etc. Okay, next one. So, what do we know? It's getting warmer. We do contribute to it. You asked me over lunch on Monday, Stefano, what I think about these questions these days. Okay, we do contribute to it, so we should act as best we know we can. Next one. What do we know less well? By how much is it getting warmer? How we contribute to it? How does the climate system really work? How does natural variability interact with forcing? Next. To do better understand the system and its forcings, explore the models of the system's robustness and sensitivity, which involves stochastic structure and statistical stability and linear response and response function. Susceptibility function, which is Fourier transform, response function, and I think the next one is just a bibliography. Okay, so this is taking a little longer than I thought. I wanted to leave more time for discussion, but in any case, I mentioned these two books. This is something that has to do with this generalization of bifurcations, tipping points in open systems. This is a book which is as readable as Ludwig Arnold's is not, okay? It's really very good for people who don't want to spend their entire life on dynamic systems. This is a paper that deals with the algebraic topology of the Lorentz random attractor. So there's some very interesting stuff to be said about the way that this very fascinating movie evolves in time in terms of number of holes and stuff like that algebraic topology deals with. These are the papers that I already mentioned to you. So this is the one that has the supplementary information that movie, but the low resolution form. This is a review paper of nonlinearity, and this is really because of modern physics is a fairly respectable journal with a pretty high impact factor, and it's actually the first climate variability and climate change paper in it. This I mentioned. This deals in some mathematical, rigorous mathematical detail with critical transitions, behavior essentially around bifurcation points. This is an example that we're going to come back to in the last lecture next Wednesday. This is one of these, I cited that one figure out of this fourth assessment report on summary for policymakers, and this is paper from the snapshot track to school, and this is an application of message time distance to big cloud models. Okay, so that's it for today, and we can still talk about it.
Yeah, this case, just suggesting that the environment is some linked to the random factor or not.
Well, look, I think that one of the reserved slides deals with the answer to that question. Can you run a little bit down? Oh yeah, that's a problem for you to, sorry, bring that back. Okay, so, remember problem 2 is about computing the Lorentz butterfly, problem 4 about doing statistics, and problem 8 is just try to reproduce some of today's stuff, add some noise, compute some sample solutions, invariant measure, and sensitivity to parameter changes, although this might be a little bit more than all that. Okay, but let's keep going then. I wanted to get to observe. Oh, yeah, okay. I couldn't resist. This is actually, I didn't do it for the lecture here. I did it for another talk, but I love it, So the translation is in English for those who are not Italian. Given the fact that Galileo was born in Pisa, etc., la filosofia è scritta in questo grandissimo libro che continuamente ci sta aperto innanzi agli occhi. Io dico l'universo, literally, but let's look for the thing about deterministic and stochastic. Oh, and this is another one this is from another place. Questions of science, authority of 1,000 is not worth the humble reasoning of a single individual. Well, clearly, we had a little bit of trouble with that problem. A little bit of that issue. Next one. Oh, this is about structural stability. Forget it. Next one. Well, this is a more modern version. This is something about aerosols and greenhouse gases. Okay. Further. This is in greater detail about the mental model and about parameter dependence in big models. But I think that somewhere, this is about something that we're going to work on, Stefano. We didn't. Okay, so these are some more sample measures. Sorry, these are, I should have taken out some of these. One more. Yeah, this is it. Yeah, I don't have the right one, but when I gave the talk at RIMS in Kyoto, I had one about deterministic and stochastic. I'm sorry. Nature is not deterministic or stochastic. models of nature are, depending on what you want. Clearly, if you want detail, you need details, you need to be treated as deterministic. If you can make do with moments and so on, then you use stochastic. So I've run out of problems that I can deal with exclusively by deterministic models. That's the short answer to your question. Yes, I think that combining, nonlinear drift with some stochastic processes is helpful in understanding some of this stuff.
Okay, but the random attractor, how should be interpreted?
Well, look, I think that Franco Fanta was working on trying to, I mentioned already, at least it was 2 years ago when we had that Pinesta incident between Henri Poincaré, defining climate and weather. It's very hard to define climate. If you want to take an infinite time, then you cannot change it. So that's not very good. Okay? If you want to use, like in statistical physics, an ensemble, that's not very useful because we only have one planet. Okay? I had another quote, which is also not included in all these reserved slides, from, but I had it in one of the other talks, from John von Neumann. So aside from all the other great things that John von Neumann did in physics and mathematics and economics, whatever, he also basically started numerical weather prediction. He called to the Institute of Advanced Studies in Princeton in the late 40s a group of meteorologists, and they performed the first highly idealized numerical weather forecast for 24 hours. His associates were Charlie and Hartmut Fjordhoff, the Norwegian meteorologist, and they showed that very simple model, perfect, whatever, could do changes in configuration that looked something like in nature. Were certainly better than what Richardson had done during World War I. So, but then he was also interested in actually modifying climate. He had this idea of the weather system in phase space having some saddles, okay, some fixed points that both stable and unstable directions, and he thought that you might be able to react this stuff by suitably exploding atomic bombs at these points. Well, he unfortunately died rather young in his 50s, and the book that was published out of this meeting called Institute for Advanced Studies in the 50s was only published in the 60s. But what he said in the introduction to that meeting, it's the one in which for the first time the words climate and dynamics brought together, was, the initial value problem was easiest. The asymptotic one is next easiest, and the really difficult one is in between. Okay? So, attractors do not exist in nature. Nothing that would, the mathematics that you do exists in such a nature. The question is whether we can find out, and going back to Galileo, to that beautiful quote, you can try to understand using those symbols as he put it at the time, circles and triangles and so on. You can understand something. Without them, you understand nothing. With them, you maybe understand something. All I can tell you is that I think, and a few other people in the meantime think, that using these tools can add to our insights into what we're doing to our planet, and maybe help us fix it. Less philosophical questions. Yes?
One curiosity. When the people make simulation to predict other global temperatures, use a mathematical model, how many degree of freedom there are? How big are the model? How many degree of freedom?
Well, the models, I mean, you know, of course, by now there are so many different things that are computed. As is well known, one of the biggest wastes of energy by humans is to issue cryptocurrency. Okay, and I don't know, you know, and then of course the National Security Administration of the United States is spending a lot of time and compiling data and probably the Chinese counterpart will do more. But these GCMs or ESMs are some of the largest users of computer power, of civilian computer power. In other words, aside from the NSA and cryptocurrency. So it's you know, hundreds or thousands of millions of variables. So each one of these exercises of the assessment reports, which involve now what's called the CMIPS, Climate Modeling Intercomparison Project. So the previous AR6 used CMIP6, and now there's another one being outlined. You know, there's a protocol. Anybody who wants to participate has to do things a certain way. I don't know exactly how big those models are, but they're really mighty big. And for the first time, there is an attempt of, you know, there have been, aside from these periodic reports, also special assessment reports. So for instance, there was one on extreme events recently. And then there was a famous one on 1.5 degrees versus 2 degrees, which I find a little bit insulting to the intelligence because, you know, there were columns of numbers, said 1.5, then, you know, sea level highs will be 23.5 centimeters, and if it's 2 degrees, it's going to be 17.8 centimeters. Well, you know, using 3 digits when you're talking about something that you know so little about is not exactly what Lord Kelvin or whoever, Lord Rayleigh would have thought is right. But for the first time, we're talking about having a special report on tipping points, because these big models are not particularly good at reproducing catastrophic behavior because they're tuned. You know, how many semi-empirical parameters do you think that one of these high-end models has? 3, 10, 1,000? Also one of my favorite questions. Well, it's probably about 100, and since people, you know, how do people tell that the model is any good? Well, they look at how well it reproduces that and how well it reproduces the other things. But it's only fairly recently that systematic metrics have been used. The metrics in this field don't mean what they mean in mathematics. You know, they don't have to satisfy the axioms of a norm of a metric. They are just numbers that characterize the behavior. So since this has been started to be done, something like 30 of these are considered to be really important. And there are things like friction coefficients with the surface or between the planetary boundary layer and the free air, lots of stuff like that. So it's a little bit difficult to expect unexpected behavior when you have fitted 100 or 30 parameters to past climate or present climate. Okay? So there is a feeling percolating that these ideas that look exotic might be helpful in deciding what might happen that is not tuned to the past. So there is a paper that has been accepted and is about to be published in Environmental Research Letters, which is also a pretty good journal, that involves one of my former postdocs, Nicholas Burrs, who's now a professor in Munich, and the third author is Thomas Stocker, who was co-chair of one of these working group 1 reports and really active out there in the politics. So maybe by the time you're hopefully gainfully employed as a researcher, there might be some scope for using this stuff that impacts real behavior. Okay?
Thank you. This outcome is Sandro seminar, and in some sense, your seminar will be about the difference between this teacher and this teacher, but for extreme events. Something like that.
Yes, for math, not for
Yes, in another place, but there is a link with something that we see. Okay.
I'm very happy that Sandro will give you something that is full of mathematics.